In this video, we're going to derive the formula for the simple case of a volume of a solid of revolution. And so the first thing that we should do is make sure that we understand exactly what a solid of revolution is. So we're going to look at this case here, case 1, the simplest case, and we are going to look at the solid that is created by taking the region that is under the graph of f of x from x equals a to x equals b and revolving it or spinning it or rotating it, call it what you want, around the x-axis. So that's a very, very specific situation. There's going to be more cases later, more complicated cases in geometries, but we're going to look at this very, very simple case first. So let's take a look at our region here. So here it is. Here's our region that is under the graph of f of x from x equals a to x equals b. And we're going to imagine that this region is revolved or spun around the x-axis. So that means it's going to come out towards you, go down below, go back into the page, and then come back out. And if we imagine what that looks like, it's going to spin around and create a three-dimensional object here. It's going to create this solid. We see our original function f. The function f, when it hits the bottom, here's the image of f down underneath. It's coming out of the page, back into the page, and creating this three-dimensional object. And so our goal in this unit, our goal is to calculate the volume of this solid. That's what we want to do. We want to be able to calculate the volume of this solid right here that has been obtained in a very, very specific way by rotating the graph of f of x, the region, I guess I can call it the region R, rotating that region around the x-axis, okay? So the way that we're going to proceed is like we did for area, which means that we're going to start with an approximation, and then we're going to make our approximation exact by taking a limit. So what did we do for area? So for area, when we had a graph y is equal to f of x, we approximated that area using rectangles, right? So we took rectangles here, we evaluated the height of those rectangles, we created a Riemann sum, we took a limit, and that limit gave us area. So we're going to do exactly the same kind of idea with volume, but we're going to approximate volume by disks. So disks are these slices here, right? That is one disk. And you're going to imagine slicing up your solid like you would slice a loaf of bread. And each of the slices gives a certain amount of volume, and if you add up the volume of each of those slices, then you're getting an approximation for the entire solid, right? So I say here, imagine adding up slices of bread, and that will give you the volume of the entire loaf. Okay, so that's our plan. The question is, how are we going to go and create these disks, right? How are we going to do that? And so we're going to inform ourselves by our rectangles from before and see if we can't create disks out of them and proceed to add those up and take a limit. So if we go back to the original picture and we add in a single rectangle, right? So over here we've got one single rectangle. Let's call this the ith rectangle. And it's one rectangle out of many, but it gives us the idea of how to create a disk. And so that rectangle we know, or what we did is we created this. We created the base of the rectangle was delta x, which was b minus a over n. And the height of the rectangle was this distance here, right? It was the function value because there was no lower bound, it was the x-axis. So we have talked about an area doing top minus bottom. The bottom in this case is 0, so the height ends up by being just the function value. So that is one rectangle. And if we imagine that rectangle being spun, being revolved around the x-axis with the rest of the region, well, what does that one rectangle create? If that one rectangle is spun around here and then comes back to its original position, well, what does it create? It creates a disk. Right, so that single rectangle creates a single disk. Right, we look at the xi, it's in position right there. The delta x is still that width right there, and the height of the rectangle now becomes kind of the radius of the disk. Right, the height of that rectangle right here, right, the height of that rectangle right here has become the radius. It's the exact same height, the radius of that disk right there. So what we want to do is calculate. We want to calculate the volume of a single disk. We want to calculate the volume of a single disk and then add up the volume of all those disks and eventually take a limit. So we're going to look at the volume of a single disk. And it's this is the disk here. If I just take this disk and flip it sort of over on its side so we can get a sort of clearer picture of what things are looking like, the volume of a single disk, which I've called the ith disk, the ith disk out of many, well, the way you calculate this is the area of the base times the height. The area of the base times the height. And the area of the base, well, what's the base? The base is this. And that base is a circle. And so the area of the base is pi r squared. And the height, well, what's the height of the disk now? Well, the height is this. And so that height is delta x. So pi, well, pi just goes there. The radius we said, right, this is the radius right here. The radius is that function value. So that function value, pi r squared, so pi f of xi squared, times delta x. There you go. So that is the volume of a single disk, the ith disk. Now, that's not enough, right? We want to approximate the volume of the solid by adding up the volume of n disks, where n is just some arbitrary but fixed number. So, all right, that's fine. The volume of the solid, V, these should be approximate marks, right? The volume of the solid is approximately the sum of the volumes of the individual disks, which means that we have the sum from I is equal to 1 to n of the formula that we had up here. So pi times f of xi squared times delta x, which is already beginning to smell a little bit like a Riemann sum, right? And so what do we need to do to make it exact? And that is to let n go to infinity. N is the number of disks. I don't want a fixed number. I want an infinite number to make my volume exact. And so if we take the limit as n goes to infinity, we get the exact volume. So the exact volume is the limit as n goes to infinity of the volume Riemann sum that we had up above. And now that we have a limit of a Riemann sum, well, we have exactly a definite integral. So the volume, the exact volume, is given by this integral, the volume of our solid. This is a very, very specific type of volume, remember. This is the volume of a solid that's created by revolving a specific region. What region? Under f of x from x equals a to x equals b around the x-axis in that very specific case. Then the volume can be calculated as the integral from a to b of pi times f of x squared dx. Okay, so let's go and do an example of this easy case formula. So let's do the region. So our example here says let R be the region under f of x is equal to the root of x on the interval 0, 1. And let S be the solid created by revolving this region R about the x-axis. We're asked to sketch R and S and sketch a typical disk and then find the volume of S. So let's go ahead and do that. So here's our solution. So let's set up a couple of axes here. So we are looking for this region R. So let's sketch the square root function. So here it is. Y is equal to the square root of x. And we are looking on the interval 0, 1. So 0 is there. And then the region that we're looking for, our region R, under that curve, which means bounded by that curve and the x-axis, here is our region R. Now we're imagining this region being revolved around the x-axis. So if we go ahead and draw our solid S, we're going to recopy our curve on top. And then we're going to imagine that curve being rotated around. So that curve, when it hits the bottom, right, it's going to come out of the page at us, and when it hits the bottom, it's going to fit down there. And so this is going to give us a solid that looks like this. And so that solid has, right, a volume. It's been revolved around the x-axis. And we've got this volume which kind of looks like a wine glass. A very pointy wine glass at the end, but kind of wine glass-like. And so if we're going to sketch our disk, we're going to imagine a single rectangle, right? A single rectangle here that is going to get rotated around. And so that is going to give us a single disk. Here, the rectangle becomes the thickness of that disk. And there's our single disk. We know that the width of that disk is going to be delta x if it's a single rectangle, but we know that that's going to become dx when we go to the limit, when we take the limit as n goes to infinity. We know the radius. The radius here is going to be the function value. So our radius here is f of xi when our radius, our rectangle was joined at position I, xi. And so this is the solid S drawn with a typical disk. So we've sketched R, we've sketched S, and we've sketched a typical disk. So now find the volume of the solid. Well, that volume is going to be given as the integral from a to b of pi r squared dx. That integral is the integral from a to b because we're in this very specific case of a region under a function. From a to b being rotated around, though it's pi f of x squared, filling in the values that we know. We know our a value is 0, our b value is 1, and our function value f of x is the square root of x. So this becomes the integral from 0 to 1 of pi times the root of x squared dx, which is now really easy to evaluate. I'll pull out the pi, so the integral from 0 to 1. If I square the square root function, I get x dx, which FTC part 2 tells me I can find an antiderivative that I want and evaluate it from 0 to 1. Antiderivative that I'm looking for is 1/2 x squared, and so pi times evaluate at the top, 1/2 1 squared minus evaluate at the bottom, 1/2 0 squared. Nice, easy, simple calculation here that's going to give me pi over 2. And this is a volume, so that is really in cubic units. Okay, so there is the volume of this solid of revolution. That is the easy case. We're going to proceed to more difficult cases in just a bit.